Hey everyone, good to see you here. I think I'm about to hear myself. There we go. Yep, stopped before you heard me, but you might hear the banging on the ceiling. They're working on the roof. 475 got to experience that. Ah! Yay, fun times here. Would you be able to go over 475 4G? Yeah, we'll take a look at Andrew, you bet. And Dalen says, not homework if you have a shiny question. Santa's back. Santa. Oh my gosh. Priya wants some Canvas content. Let's get the notes going right here. Oh my gosh. Santa's over there right now. Santa was up there. He's over there now. But we'll, hopefully we don't hear Santa too much. So let's take the notes right here. Put a little chill music on here so Brian can concentrate. Amazing. It won't be happening next week. Santa's going away. Santa's a this week only thing. Santa's only visiting this week. Sorry if you're watching this video later on in the evening and you hear some, you'll probably be wondering what the heck's going on. Watch Brian Mike's popping every 2 seconds. Santa's here. Final assignment. 4G. Shiny question. Discard the repo and the slaughter rail is the file. I'm afraid I have another bench, but I want to check to see if you. Yeah, Dylan. Sorry, Dylan. We'll check that out. Might do some project. Let me put that on here. Shiny repo question. I might be able to. I'll probably check it out this weekend because I'll need to load up the repo. But yeah, your slider thing is really awesome. And the way you have it re-auto correcting. Oh my gosh, that's so crazy. You're welcome. Yeah. Canvas. Is that Canvas content number 8, Priya? Canvas content number 8. We'll take a look at some models here in a second. Take a look at some models. Gonna get the data up and going. How's everyone's day going? Is everyone having a good day? We're gonna get 4G up. Some 4G. All right. We've got a bunch of... we can leave that open. Where is the final assignment? My R did some weird stuff earlier. My R was like crashing and not good. Let's go down here to 4G. That's really nice of us. That's very, very nice of us. So what we need to do, let's go to 4G. Canvas content number 9. Not number 8. Why not number 8? Canvas content number 9. Yeah, no worries, Dalen. I super cool. Yeah, no, definitely. We're gonna do some. So let's work on the assignment here. Stretch. Got up early this morning to Santa. Santa, please go home. Please go away, Santa. Please go away. So let's see. I'll make sure I have all the components of what we need. Get all my stretching out of the way right here. Make sure. There we go. Yes. Let's go ahead and take a look right here and go ahead and start up some 4G. Here we go. Taking our timestamp down. This is BAS 475. So we're doing some time series right here. 350 in on the time series. Now, when we look at 4G right here, we're actually seeing how we do. Now, if you look at the way both of these are computed, we were doing this in class today. Did we do it over here? We did. Perfect. So it's the same sort of thing done for you. All you're doing is taking it and turning it into a function. This is something we practice in 475. Grabbing everything right here and taking. Now, when you look at your RMSE, what do you need? And if you're in Tool 1, you'll remember these terms because we don't usually call it things like RMSE. This right here is known as a residual. So what components do you need? Theoretically, what do you need to find your RMSE? You would need a few things to find your RMSE right here. You have to have these things, which you can see it as we solve this. So what do you need? What would you actually need right here? What would you need as components? I'm on top chat still. Exactly. You need your predictions and you need your actuals. Exactly. As you can see by the equation, residual equals actual minus predicted. And then right here, you would go and just use the residuals. It's still just the error. Usually we call it R for the root, mean squared error, RMSE squared error. And so now we would go up here and we need to put into this function that we would need to take the predicteds. So we can call this RMSE function or whatever, and we could create the function right here, and then this would take the two vectors and solve for us. I've already created a predictions vector and an actual vector. Oh, no predictions found, didn't store them. There we go. And there it is. So now this would run and do the work for me. Does this make sense, Andrew, right here? Like, this is the idea of creating a function. I think I've got it indented properly. But this is what you're seeing supplied to you, which is something we should probably practice doing it. Like, we maybe should have asked you to build the function. That way we get you more in the habit of like creating a function if you have to use it, because maybe you want to find the RMSE multiple times. There is a package also that does RMSE for you. I'm trying to think what package it is, but you could build your own function. You could go find something, just write the code to do it. And the code for it is find your residuals, then find the root mean squared of the residuals. Same thing works for mean absolute error. We could literally just turn this into a function also by going here to fun, dropping in the code we have, and then just taking the predictions and the actual. We can call this MSE function. And then, oh, we got an error. Where's our error? Whoa, what's going on? Oh my gosh. There we go. And then with our MSE function, the same sort of thing could be done right here. But is everything I'm doing right here making sense? Yes, it does. How do I get the actual points? I have already my predictions. Yeah, 474, you write a lot of functions. Got a lot of practice on that. So with this right here, through this assignment, you should have, because you held out the data, right? So you should have the holdout data, right? So, because I don't want to do everything. I want to like show it. Because you're making predictions on the holdout, right? You're using your fit on the holdout. You want to take your model and then forecast on the holdout, right? So where would your, so this kind of leads to it. I think you'll find it now and be like, oh, because watch this. You got something called holdout, right? I don't think I have a holdout right now. But inside your holdout is what? Boop, do that. And what do you see? Oh. So notice right there. Oh, look at that. Did that do something, Andrew? So, ooh. What do I got right there? Should have some vectors, right? And those are the answers to what we have. So that will be the what? Your holdout data. It sounds like you have the predictions, right? It did, right? So now take the y variable you're trying to predict right here, whatever the y variable is of interest, and you could just store this into actual. You could just go right there, and do the actual data, exactly. And then from your fit, so make sure you've done the fit, you could go here and do predict, and you would need to take the values from the predictions. So this is from earlier, I think it's the previous question, where you're storing your predicteds into here. So this is going to be your predicted values right here, store predictions here. Make sure you've untransformed them. So they do untransform themselves if you use a transformation in the model specification. Adam and I were going over that today. So you can do that. So make sure you're either untransforming them, store the untransformed, store the predictions here, store the untransformed. Make sure you've untransformed them. I like to call things just actual and predict. It's just different names. Now mine won't store, but here's the thing. Once I've created all this, I can just go down here and do RMSE, which I don't even have this function yet, I don't think. Those will just specify the functions. And from here, I can just input the actual and input the predicted. How's this looking, Andrew, right here? And then I can go here and get the MAP, which I don't usually find, mean absolute percent error. So it's divided over. So it's a percent error that it's away from the actual. So you're doing it based on the actual. Think about this mean absolute and then the percent error you're away. So that's how you calculate. Yep. Nice job, Andrew. Yeah. Basically, how is it untransformed when we use box Cox? I know we talked about it, but I'm blanking now. Depends on what lambda you used. So there's the inverse box Cox. So inverse, we should have an inverse box Cox function. Inverse box Cox. There it is, inverse box Cox. So we need to specify our vector. I think I have an actual vector store, right? No. I thought I had some fake data in here. Let's go take these predictions. So here's our predictions. And it's going to use a fake lambda. No, it didn't. It's mad I don't have a lambda value. Lambda equals 0 is going to be the log. There we go. So it's using natural log, right? Because my predictions right now are that. Yep, and there's 2.71828. So it's using, that confirms, yeah. And so that'll undo, but make sure you specify your lambda. Lambda 0 is natural log, hence when you untransform 1, it's transformed back into the log value because you've natural logged this value. This is the untransformed value. Using a lambda of 0, use a natural log transformation, and thus 2.71828, all that good stuff. Yeah, 1F, definitely. Good questions, Kayla. I'm just going to fall off my chair here. They finally got off the roof. We had a visit from Santa. You can tell all the kids, Kayla, that your teacher, Dalen, can confirm, and Andrew can confirm, Santa visited our last class. More importantly, Santa was here to sell us stuff. I don't know why Santa's trying to sell us stuff, but I think it's quote 209 from last class. We had a visit from Santa. Yep. He definitely was here, 100%. I should make some Santa image. He's real. Oh, going back to the main screen. Oh, go back to the main screen here. Okay. I got some sparkling water today. Everything's good. I think we're about to do Canvas content. Yep. Number 1F, assignment 11. BS. I think someone just fell on the roof. Santa, you okay? Canned water, always good. Are you there, Santa? It's me, Brian. They woke me up this morning. They're working on the roof. Up on the rooftop. Bang, bang, bang. Okay. Canvas content, then we're doing homework 11. Canvas content, then homework 11. I had some mocha Oreos. Mocha. It's pretty good. HEB with all the Oreos. HEB has everything you'd ever want. Canvas content number 9, the second to last Canvas content, hypothesis testing. Good stuff. Santa, stop it. I'll take the roofers any day. Oh, yeah, let's take a look here at Canvas content number 9. Timestamp this. Here we go. Hey everybody, if you are watching this video right now, I have roofers working on my roof. So if you hear banging, it is the roofers. So thank you for watching this. And you could hit like if you want, or hit dislike. Either which way, it doesn't matter. Let's work on some Canvas content here. So a new diet is being tested. The inventor claims, people invent diets, that people lose 10 pounds on average for 6 weeks. 25 people are randomly picked to try the diet. Researchers, sounds like people just really want to hear about this diet, are concerned that the inventor's claims are exaggerated. Now, whenever we write a null hypothesis, what will the null always have? And this makes our life a little bit easier. Like if we got this as a test question, we can narrow this down pretty quickly. Whenever we write a null hypothesis, the null always has this. Like you can be like, I got this going right here. Priya's got right there, the equal sign. So we've literally just narrowed it down to boom, boom. Now we're between two answers, right? So if you're on a diet, you probably want to what? So if you're on a diet, you probably want to what? Now be careful. Well, I'm gonna try to deselect it. That's not the answer. But if you're on a diet, you probably want to what? Just talk to me theoretically wise. So theoretically, you want to lose weight, right? It makes sense. That's why usually people diet. I guess you could say I'm on a diet. I'm trying to bulk up. You know, a lot of times people talking about people claim you can lose 10 pounds on these diet in 6 weeks. That's doable. Please make sure to treat your body right and eat well, depending on your hashtag goals right there. Doable. Someone says you're going to lose 20 pounds in 6 weeks. I say, I don't know about that. You got to watch out. Got to make sure your body's getting the nutrients it needs and, don't just, be healthy. Treat yourself well. I can't spell either. Don't worry. Lost weight. I like it. So the problem is we're looking for the what of the alternative right here. when we do this, the null always has the equal sign. So we always say what we're testing, the true mean weight loss for diets, a quantitative variable, mu, is equal to the hypothesized amount. Thank you, roofers. And then we would have right here that we are looking for the what of the alternative. Because we're only between these two because it has to be equals for the null. The null is always that you say equals to this. So we're looking for right now for the what of the alternative. We are specifically looking for the what of the alternative, which is worded by the question, the sign of the alternative. So now be very careful. I think people could get this wrong because the researchers are worried the claim is exaggerated. So the researchers would want to show evidence that the true mean weight loss is what to 10 pounds. They're saying, we think we can show that these claims are exaggerated. So think about how you would just talk to someone. The researchers are trying to show evidence. Oh, thank you, Kayla. That gives me a lot of confidence. I appreciate that because I can hear it. For me, it's a lot louder. So do you think the researchers want to show that they can lose more than 10 pounds? The researchers want to say, we're going to show that you can lose more than 10 pounds on this diet. So the researchers are trying to show evidence of what? So the researchers are worried that it's exaggerated. So they're trying to see, show that these claims are exaggerated. So if the claims are exaggerated, the researchers would want to show what? That's a fake diet. Yeah, they want to show that you'll lose less than 10 pounds. That's what they're looking for evidence of, right? So they're saying, is there evidence you lose less than 10 pounds? You lose 10 pounds. And the researchers are like, we don't think you'll lose that much. We think there's evidence. And this is what they're trying to show evidence of, that the true mean weight loss. No worries, Dylan. Oh, it's all right. Another new diet is being tested. All these new diets right here. We're going to copy paste this question right here. Thank you, Kayla, for giving me a moment of sanity right here. I don't want car insurance. I'm happy with my car insurance. A new diet is being tested, the insurance claims, and we need to channel our inner Leo. Leo, where you at?
Notation, brother.
So who can help me with any of the notation on this? Any of the notation. Oh, thank you, Priya. What is any of the notation? Any notation right here. Any notation. I should just go with it. Yeah, Maria, I think we definitely will. Great job, Kayla, right there, practicing some standard deviations, 100 points. Oh, yeah, there. Ooh. That's Y bar. That's S. There's N. So it says calculate the test statistic. The notation scared you a little bit. I like it. It's our new thing from yesterday. So with this right here, the notation is going to actually lead us through this because this problem is not so bad. This one is just plugging in the numbers and solving, and we can almost do it in our head. Oh, we're missing one value. We are missing one value. Ooh, 500 points. I'll give it about 10 seconds. What value are we missing to run a statistical test? We're going to plug them in. We're missing one value, though. I missed one in my marking of notation. See if you can get it. It's a good one. We need it to do the test. I'll write the notation down here, and I'll see if you can find it. I'll write the statistical test. Mu naught. Boom, right there. Did I say 1,000 points? I think I did or something. Priya, you got it. That's the hypothesized. Great work there, Priya. That is the hypothesized. 10 is mu naught, technically, because that is the hypothesized claimed truth. So that is mu naught. And then the null hypothesis would be that the true mean is equal to that hypothesized value, which is 10 right there. And Priya, just doing great. Thank you, Kayla, right there for all the support. That's what we do right here. And then they're worried it's exaggerated, so it's still the same alternative. And notice this is 201, yeah? Good practice of 201 and knowing how to test claims right here. Good review, good practice. For everyone who's upper level classes, we got 320 here, 475, 201. Everyone here, it's all a party. So with this right here, let's now take and run our test and do y bar minus mu naught. Now, when we do statistical tests, the top of the equation is just a what? The top of the equation is just a what right there. In statistical tests, the top of the equation is just a what? We're going to write in the numbers there in a second. And then we're going to go S over square root N. It's just a difference. Priya, Rockstar, great job. It's just a difference right there. We're just seeing how far are those numbers apart. And then the bottom of the equation standardizes that difference. This is how we standardize it. So it's just a difference divided by a standard deviation or a standard error in this instance. So that is the standardized difference. And we're just going to plug in our numbers. So we're going to take a difference up top, our sample mean of 0.3, which is nothing, minus 10 over, and S is 6.7. That's a huge standard deviation over square root of 25, which is 5. So this will just solve, once again, you're just solving this equation right here to get the t-score with n minus 1 degrees of freedom. I guess we missed one more bit of notation. While I solve for this t-score, who wants to say what the last bit of notation was? Great job, Priya, right there. I think Priya's got it. I'm going to plug it in just so people can watch the mathematics, but I'm pretty sure Priya just got it. 6.7 divided by 5. There we go right there. And then 0.3 minus 10. And Priya even remembered the negative. Great job right there. And the only other thing we didn't mention was the degrees of freedom. The degrees of freedom would be 24 degrees of freedom because this is a one sample t. And the degrees of freedom right here are n minus 1, which just tell you which t you're using. Now, it wouldn't really be fair to say what is the p-value on this, but the p-value on this, which it doesn't ask, great job, Priya, excellent work. The p-value on this, yeah, go cook, and we'll be doing some assignment 11 here in a moment. Go enjoy. The p-value on this is going to be basically 0. Like, it's not even going to show up. We're doing the less than test, and the p-value is way off the scale. So we don't write a bunch of questions where you kind of have to know it theoretically. Usually you'll see questions about like this t-score and stuff that you have to find, but the t is so far off the curve that you don't even see the p-value. So not happening. That is a p-value of basically 0. And so great work right there, Priya. Excellent job. And 2 decimals. Make sure to remember if it's negative, subtract the right. When we reject the null and the null is true, what error have we made? We reject the null and the null is true. I love this. Now, there's only how many answers to this? How many answers, if you get to this, how many answers can you narrow it down to? So you see this question, and you're like, okay, I have to narrow it. Let me try and narrow it down, use my knowledge, and be like, I can narrow this down a little bit. How many can you narrow it down to? We got this. Oh, well, I think Priya's answering the question. Great job, Priya, right there. And there's only 2 possible answers, right? So there's 2 answers. One of them is right. But with there being 2 answers that we could narrow it down to, there's type 2 and type 1 errors, right? So in a type 1 error, the null is what? We covered this at the very end of last classes. And if you were there, there we go. Kayla knows it. Kayla's just like, boom, I'm making dinner. But type 1 error, null is true. Boom. In a type 2 error, the null is false. That's an F. And we fail to reject it. So knowing that the null is false and we fail to reject it, if you know that you get to this right here, in a type 1 error, the null is true and we reject it. So if you know that by doing type 1, null is true, that's a T, 1, T, 2, false, false. If you practice that and memorize it, especially just with the practice type 1, null is true and we reject it, type 2, null is false and we fail to reject it, you'll know that when the null is true and we reject it, that's a type 1 right there. Good memorization technique on that one. Type 1, null is true. Type 2, I know. Hannah thought of that from our department a long time ago. Got to give credit to Hannah. A, B, C, or D. I'll let you figure this one out right here. We're just getting random questions right here. A, B, C, or D. This is where you're like, really, Brian? So easy. I know, the 2 F's right there, right? Priya's like, got this. The null hypothesis is false and we failed to reject it. Because why? And people are noticing, what do you notice about this statement right here when you have a type 2 errors? Type 2 error, and you always talk about the null. We don't say anything about the alternative. In a type 2 error, there's 2 whats? Because in a type 1, the null is true. There's 2 F's, right? The null is false, and we fail to reject it. And it just works because you can make it. So I've just found that is the absolute ultimate way to learn that concept. I've had other teachers take it from me in a good way, like that they've learned it. Pretty sure you ran out of time mistake. We do 1A. Yeah, we're going to be doing, yep, that's what we got next. You got it, Kyle. And thank you, Kyle, for being here. 100 points in the chat. And last but not least, low p-values are evidence of a cause and effect relationship. What are people's thoughts on this? If the p-value is low, cause and effect relationship. True or false? We got a good version of this. False. Priya, great work, because we can't say things are cause and effects. It would be evidence of an association, but we can't say things are cause and effect. Cause and effect is something stats really doesn't do. We don't talk about prove. We don't talk about cause and effect. How do we do on all that rounding? Hopefully we did all right. Maybe we rounded something weird. 10 out of 10. If we construct a 95% confidence it does not contain the hypothesized value, which the statement is true. So if you construct an interval that does not contain the hypothesized value, what would that mean you would do to that value? If your interval does not contain the hypothesized value, do we not have any slides over that today? If you construct state list of banned words, if you construct an interval that does not contain the hypothesized value, what would you do for Klondike bar? So if the hypothesized value is outside the interval, if the hypothesized value, what is going on? Oh, wrong thing. There we go. If the hypothesized value, i.e. this value right here, is outside this interval here, notice how I know it's like just barely, but it's outside the interval. If the hypothesized value is outside the interval, you could what it? So if we have a hypothesized value that's outside the interval, we could what it? What would we do with a hypothesized value that's outside? It's like my friend Leland. We talked about him a lot yesterday. I need to send him the video. We tested Leland's mile time. He was super fast. Leland, turns out we got an interval estimating Leland's mile time between 3.7 to 4.4 minutes. But now Leland says, Priya's on the right track. Leland says he can run a 3-minute mile time. So Leland claims his average mile time is 3 minutes because he's just being awesome, trying to be awesome. So what would you say to Leland? I think your true mile time, Leland, you're very fast. I think your true mile time is somewhere containing the interval 3.7 minutes to 4.4 minutes. And thus, your claim of 3 minutes is whatted. Just talk to him like, oh, yeah, cause is, oh, yeah. No, we don't say that here. We don't say cause. We don't say except the null. Got some banned words here. What would you say to Leland? Like, talk to him, be like, dude, your claim of 3 minutes, you can run a 3-minute mile? I think your true mile time is somewhere, I'm 95% confident your true mile time is somewhere contained in the interval 3.7 to 4.4, your true mean mile time. I'm 95% confident, Leland, that your true mean mile time is contained in the interval 3.7 to 4.4. If I talk to him normally, I'd say, you're probably about 3.7 to 4.4. I reject this, Leland. What you're offering to me as an idea, I don't think that's true. I have evidence for the alternative, another belief. Oh, that's the worst handwriting I've ever done. I have evidence for an alternative that your mile time is not 3 minutes. Does that make sense? I know he's super fast, but he's not 3 minutes fast. He's not breaking world records. Close. 3.7 is kind of close. But he's not there to that 3-minute mile yet. Awesome. So we would reject it. Anything outside the interval can be rejected at a point. Excuse me. Anything outside the interval can be rejected at 1 minus confidence level of alpha. And we went over this a lot yesterday, so check out where I go into more detail talking about how when you find the alpha level, it simply works this way. If you make a 90% confidence interval, it would be the same as using a two-tailed test with what alpha level? 90%, some test questions ask things like this. 90% confidence would be the same as doing a two-tailed test with what alpha level? Just look at the visualization and be like, oh, and then look at the math right there. So 90% confidence would be the same as running a two-tailed test. It would come to the same conclusion on reject, do not reject if it's contained in the interval, as a two-tailed test with what alpha level. So think about how it's like, oh, inside, outside, 100% of the curve. So what would be the relative alpha level if you're using a 90% confidence interval if you did a two-tailed test with the same relative alpha level? So if 90% is inside, think of the complement. The alpha level here, which is when we would reject. Oh, wait. So think about this. This curve is 100%. There you go, Kayla. You got that. Look at that. Kayla, great work. Yeah. 10% alpha or 0.10 alpha. And that's what that equation is showing you up here, is that both of these add up to 100. It's just 1 minus confidence level is 100% of the curve. And notice how it's just the outside of the curve. So the two-tailed test is analogous to doing a confidence interval. They'll come to the same conclusion. So you see how because confidence intervals are two-sided, they correspond to a two-tailed test. So it's talking about the two-sidedness of the confidence interval right here, how it has two sides to it. That corresponds down here to the two-tailed test. So you really just have in the middle of this the alpha level, or the remaining portion. Well, we did 90%. But good work right there. Shreya, good to see you here. We're going to work on some 320 now, so let's head back to the main screen. Wrong screen. Okay, good work, everybody. I've got a lot of 320 questions. Just got people... there's a wrestling match on my roof today. Big wrestling match. Hulk Hogan's up there.
Notation, brother.
You can hear him. We got 1F. Brain buffered. I thought you said Brian buffered. Just a second. Where is the other questions? Assignment 11. I thought there was we have 1F, and I thought there was a C. Go over C1. Got a C1. C1. Might be 1C. And I saw another one. Should have wrote them down when I saw them. 2F. 2F. 1A and B. Okay. 1C. I think, Maria, you were first to ask, so yours is first, Maria. Thank you, Maria. Yours was first. We have you in order right there. Okay, let me go get the assignment. It's the assignment song. Okay, I think we're good to go. Let's head over here to the main screen. And 1C. Santa, go away. Here we are on some regression, not time series. But these concepts we're using in this class will be carried over into other classes. So let's take a look at some 1C. Now, it's important to note this assignment is very much going over logistic. When do we use logistic? When do we use logistic? Why would we use logistic? This is not logistic on the screen right here. Why would we use logistic? Running all chunks above. Categorical Y, Kale, 100 points right there. Categorical Y, predicting probabilities. We'll see some graphics here in a moment. When we compare ads in the same position on the same site, viewed in the same app, all this good stuff right here, which device model, D1 through D11, you may ignore D13 since it has NA for coefficients, have the highest probabilities of a click-through rate? Is this difference in probability statistically significant? In other words, all else being equal, is the probability of clicking on the ad generally higher or lower for these devices explained? Note, you will have to run the drop one right there with the test equals chi-square. Very important right there to comment about the significance. Well, let's do similar work. The important thing to know right here, and I'm doing similar work. The important thing about this is we need to know how to do this at all times. So this work right here is exactly what you're doing, but for a different type of problem. Let's say I were to go here and I were to predict the probability. Can't think of the data set I want. Data, survey, 10, of course. And let's go here and use all variables. Make sure you're using the right model. And let's go here and family equals binomial. So make sure you specify your model properly with y tilde x comma data equals. Just curious for you. Awesome. Cool, cool. I won't need to do a repo? Okay, cool. How could I look at the coefficients in my model? How could I find the value? Who has a code for me to look at the coefficients in my model? How could I examine the coefficients? How could I examine summary? Kayla. Awesome. Okay, so let's look at the coefficients. Now, the variable I want to talk about right here is handedness. Now, we are predicting the what? And then you might think, well, we're predicting gender, right? Gender for this data set has male, female. So we are predicting what? Be very careful in understanding what we are predicting. What are we predicting? And the visualization won't work here, but we are predicting what? I'll make a visualization you can see. It's a different way of making it, but we are predicting probability of male, exactly. And the reason, oh, wrong model name. Because male comes last alphabetically, so we're predicting probability of male, putting the sigmoidal curve onto the data. And this one, the one I've created, is a multiple regression, so we can't really view it visually here. But the level of interest in logistic is last. Exactly, Kayla, good practice. And since male is after female right here, we are predicting probability of male. This is a simple logistic right here showing us the probability of male increases as people are taller, i.e. two people who are otherwise identical if it's a multiple model. The person who is taller is more likely to be male. That's simple. So let's go back to the multiple model and see something interesting. Think about this. The only thing that matters in logistic is the what of the coefficient. The only thing that matters in logistic is the what of the coefficient. The only thing that matters in logistic, the rest of it doesn't matter. The only thing that matters is the sign. Shreya, great work, 100 points right there, Shreya. So if you notice right here, this has a negative coefficient. I just want you to think about this. We're predicting the probability of someone being male. So two people who are otherwise identical, the person with more piercings is what? Two people who are otherwise identical, the person with more piercings is what? Just think about how it works. And just think about the reality you know of the world. Not saying it has to be this way. Not saying it will be this way, but just think, generally speaking, two people who are otherwise identical. I got person A, person B, they're the same. But, so wait, finish the whole sentence, Kayla. I think you're right. I think I know what you're getting towards. I don't know if you do, Priya. Good question. I'll take a look here in a second. I don't think it tells you to. I think you use the full data set. I think it does. Double check. We'll double check, but I think you're using the full data set. Two people who are otherwise identical, but one of them has more piercings. The person with more piercings, and I'd probably go with the negative interpretation. Two people who are otherwise identical, the person with more piercings is what? Try to do for the tests, good practice. You could say more likely to be female, i.e. less likely to be male. Negative coefficient means less likely the level of the interest. Usually, since it's a negative, I usually go with that, Priya, exactly. I like to say they're less likely to be male. Does that make sense? And just, does that go, once again, we're not trying to do any gender norms or anything like that. It's just, this is real data. And the way people identified in the data and the people identifying female right here, more likely to not be male. Well, that is true also. I would just say less likely because it's a negative coefficient. Does that make sense? Two people who are otherwise identical where one has, no. So you don't do it right there, Kayla. So let me interpret the whole thing. You ready? Two people who are otherwise identical, the person with more piercings is less likely to be male. Does that make sense? I'll repeat it again. Two people who are otherwise identical, because it's a multiple regression, the person with more piercings is less likely to be male. Doesn't mean they're not male, because maybe one's got 20 piercings and one's got 21, and maybe they're both male. You never know with data. But this is just the probabilities calculated by the model due to mathematical equations. It doesn't make statements about why the way the world is. It just shows us what the data tells us. So with this right here, two people who are otherwise identical, the one with more piercings is less likely to be male. Two people who are otherwise identical, the person with more piercings is less likely to be male. Boom, straight another 100 points. Yes, exactly. That's what that coefficient is telling us. But once again, we also stated that even with this model over here, we talked about the height thing. This person right here, if we put a person A here and a person B here, both these people would be predicted to be not male. It seems so short. I know, it's so easy, right? It's like, well, that's easy. Because right here, think about this. This is interesting. This is so weird. It's negative, right? Two people who are otherwise identical. The person who weighs more is what? This is interesting. This is the multiple world and why it's like you would not expect these things. And height is not statistically significant. What? What? Two people who are otherwise identical. The person who weighs more is less likely to be male. Multiple models are weird, but they're identical in everything else. Maybe it has something to do with desired weight. because there's desired weight in here more too. So two people who are otherwise identical, the person who wants to weigh more is more likely to be male. And actually, look at this. This is the second most significant thing in our model. And just think about this. Like, in the world, would you say, it's super confusing, right? Multiple models are so weird because it's otherwise identical people. So you have two people who are otherwise identical, like they're the same height, they're the same everything, and that's super significant right there. So, which might go with your idea about the world. Remember, sometimes we don't understand the world we live in, but two people who are otherwise identical, the person who wants to weigh more is more likely to be male. So pretty quick and easy right there. But now we get to your big part of this question, because in your question, you're looking at device. So if you want to figure out the most likely device for people to, I think, purchase or churn or whatever, you'd be looking at the device with the what is coefficient. The one that would increase the probability the most would be the device with the what is coefficient. If you had a whole bunch of indicator variables, I've only got this one right here, which we'll focus on next. How would you figure out which one of these is going to increase the probability the most? How would you figure out which one of these is going to most positive? Exactly. So whichever device has the most positive is doing the greatest increase to the probability, because it changes the equation by that much. So if you go to your indicator, hopefully it makes sense with your question, and look for the one with the highest coefficient, which for me, which one of these individuals would have the highest probability of being male? Like two individuals who are otherwise identical, where one is left or one is right or one is ambidextrous, which of those individuals has the highest probability of being male? Like, which of those would be most likely to be male out of those individuals with these coefficients? Now, you might say, I don't see ambidextrous, more on that in a moment. You are correct, Shreya. There would be left. Shreya, great job. Great practice, Shreya. We need to throw more points, another 500. Now, ambidextrous is interesting. And because we don't see... it doesn't matter. Correct Dalen right there. Rock, you're over-talking me, man. Why do we not see ambidextrous, and what is the coefficient of ambidextrous because we don't see it? So, Kayla, you're on the right track. We don't see ambidextrous, and why don't we see it? Now, handedness is not a Y variable. It's an X variable, making it indicators with which ambidextrous is. It's a reference level, exactly. So if it had a coefficient, that coefficient would be 0. Great job, Shreya. Shreya, you are on point today. This is where people usually lose the material, because it's a twist of what we're doing. They're like, I've done regression so much, I know what I'm doing. But then you're like, indicator variables, and they're like, indicator variables, what? So Shreya, we're throwing another 500, Shreya, your way. Great work, Shreya, and great practice. And don't worry, Kayla, you're doing astoundingly too. But Shreya, great work and good practice. Ambidextrous has no coefficient. So which one of these people would be most likely to not be male? Like, what is the thing about, be careful here. Now, because yours might be different too, because you could look for a negative one. But out of ambidextrous left and right, who is most likely to not be male? So out of ambidextrous left and right, who is most likely to not be male? We said left is most likely to be male, but who would be most likely to not be male? Out of ambidextrous left and right. Remember, ambidextrous has a coefficient of 0. Just keep remembering, ambidextrous has a coefficient of 0. So think what the other coefficients would do. It is, I think I blinked right there and see it. You are correct, Shreya. You're just on fire today. Yes, ambidextrous. Because the interpretation of this coefficient would be two people who are otherwise identical, where one is right-handed and one is ambidextrous. The person who is right-handed is what? So think about, since it's positive and we compare indicators to reference levels, two people who are otherwise identical, where one is right-handed and one is ambidextrous, the person who is right-handed is what? Remember, the coefficient is positive. Two people where one is right-handed and one is ambidextrous, the person who is right-handed is one. No, you're doing great. You're doing so X. Keep it up. You got this. Keep asking those questions. Keep answering. You're doing great. And I never want anyone to get discouraged, because it's tough. There's a lot of material. It's a lot to remember. It's a lot to practice. The two people, the right-handed person is more likely to be male. Exactly. And then up here, two people who are otherwise identical, the person where one is left-handed and the other is ambidextrous. And I keep saying ambidextrous because these indicators are in comparison to the reference level. And we know it's an indicator because the variable is handedness and then the level is left, and the variable is handedness and the level is right. So two people who are otherwise identical, where one is left-handed and one is ambidextrous, the person who's left-handed is more likely to be male. among left and right-handed individuals, we could say that the left-handed people are more likely to be male because left-handed has a larger coefficient. Remember, the coefficients increase the probability, or if they're negative for your question, would decrease the probability. So if you're looking, there might be some negative coefficients. Just remember the reference level has a coefficient of 0. But Dalen was pointing out, now Dalen, you are correct, I believe, but these p-values are the significant difference from the what? Say it one more time. So Dalen, you're right, I think, because those are pretty high p-values, but those p-values only tell us the statistically significant difference from the what. So those p-values for the indicators only tell us, since there's 2 of them or more for indicators, they only tell us the statistically significant difference from the what. So those p-values only tell us the statistically significant difference from the what. So I think the coefficient tells us its difference from the reference level. The standard error tells us our uncertainty of the difference from the reference level. The t-value tells us the standardized difference from the reference level from handedness ambidextrous. So it tells us the difference if it's different from the reference level. That's what the p-value here would tell us. So what do we have to do? We have to do an effects test to look at the effect of it from the reference level. Great job right there. Good practice. So we're going to go drop 1. And because this is categorical data, we have to do the chi-squared. It even goes back to 201 right there. So we have to do test equals, and then it should be chi-squared. I'm going to spell it wrong there. What's this? I think it's capital. Is that it? I think it did it. Yeah, it did it. So is handed... Look at that p-value. It's even worse. So handedness is not statistically significant in the model. And handedness is the only one we had to use an effects test on because handedness brought with it 2 things in the model. Anything else could be just looked at by the p-value in the model. I think the chi-squared does a slightly different calculation, so these won't match up perfectly, but still, handedness was the only one where we had to take both those coefficients to remove it out. This is also known as the what procedure for 500 points to compare a larger model to a smaller model and look if the reduction in sums of squared error is statistically significant. We're looking at a specific variable, so we can call it the effect of this variable, but we're taking our full model, removing that variable out, and comparing our model to that model. Partial F right there. Great practice, Kayla, because we're only looking at part of the reduction in the sums of squared error, where the full F, another 500 points. Kayla, excellent work and good practice. So the effects test is a partial F done, where we remove out like a whole variable, and then we compare the model to each other and see if we have a reduction. So what does that p-value right there tell us? This p-value tells us that, what about it? Including handedness. Great job, Kayla, more points. The other one's to the naive, exactly. And including handedness does not help out the model. It doesn't bring with it new information. So handedness is not a good variable, does not bring with it new helpful information to, in this instance, it would, it doesn't change sums of squared error because it's not quantitative. It doesn't adjust the model in a significant way. So we can't say reduce the sums of squared error because it's not quantitative. We don't have sums of squared error anymore. We're trying to go away from the naive model and get a deviance from the naive model, but I don't care for theory questions on that. It's just, that's bad. Doesn't help. That's like in the business world, we don't need that. You got it, Kayla. Enjoy. And good questions. We're going to do another one come up here in great practice. So that's how we use the drop 1 chi-squared, and that's how we interpret coefficients. Good work. Let's keep working away at questions. We got a few more, but if you have one, let me know. That was a good 1C right there. So let's do some 1A and 1B. We're trying to do different but similar questions to get more practice. Here we go. Okay. It is time for some 1A, 1B. What does 1A say? Fit a multiple logistic. Well, that's what we're doing. Let's go check it out. From the predictors, you will see some have an A because we can't get it due to singularities, because we basically, it deals with kind of redundancy in information. They don't bring with them enough new information so that we cannot get model estimates. Don't worry about it. But if you get additional information, examine the output. So I think we're fitting everything from all the predictors. So we've been working with a slightly different data set here. I want to make sure kind of you get some practice. Sometimes we do problems, sometimes a little similar. So how do we fit the multiple logistic? Let's make sure we know how to do that. Now, when you fit logistic, what are the 2 key changes you see right here versus your classic LM? When you're doing logistic, which means this is a categorical Y, previously it was quantitative Y, and these are just your X's. You can do the dot. But what changes do you see? The GLM 100 points right there. So first thing we see here is we're using a GLM. This needs to be a categorical variable, which we'll use here in a second. And family binomial, great job, Shreya, right there. So make sure you know that and why we're doing it. We're predicting probabilities now. The previous model was a linear model. We might have one back here. We could fit linear models through these. We were doing time series earlier, so those could fit linear models because it's a quantitative Y, but now we're doing categorical Ys, so we have to fit a sigmoidal curve. So we're doing the same idea right here, predicting gender, and let's do it. So this is all the variables. This is the twiddle dot, and you're predicting if somebody will churn, which that means they're going to leave their cell phone plan. Churn means to leave, to go away. Like I have churned, I have left. Churn to butter. Food is in the oven. Awesome. What's for dinner tonight, Kayla? What is for dinner? Do we just have to fit the model? Produce the summary, fit the model? Produce model? What's in Meadow? It's a graphics error. Boom. Produce model, summary. Good to go. Good to go. Got our model. Gonna find out what's for dinner. Kayla's making everyone dinner. I wish. Sounds good. All those enchiladas, chicken pot pie, muffin things that I saw on TikTok. Kayla, send me that. I'm going to send it to... Oh, but we could do a turkey. We don't eat chicken. Sorry, I love chicken, though. Anyways. When we compare ads of the same site, viewed on the same app, on the same device, otherwise identical, with banner position 1 or 2, has the higher probability of click-through rate. Is difference in probability statistically significant? Now, there's only 2 banner positions. So we want to use, so for this variable here, we have banner position 1, banner position 2. Do you see, now be careful, this is a good task question type thing here. Do you see, and you can abbreviate, a categorical 2-level variable in my output? Do you see, oh, that's awesome. Do you see a categorical 2-level variable in my output? Now, if it's 2 levels, how many indicators will you see? So the question is, do you see a categorical 2-level in my output? So we're going to do a similar thing right here. Do you see any categorical 2-level? But you might say, Kayla, you got it, because there'd be significant other no, which is the reference, right? So this is the 2-level, whether or not someone has a significant other. So I do, and which I just said recently. So I'm corny. I'm turning into a dad. Not literally, hopefully. But... we have significant other yes, and with significant other yes, the reference level would be no, and it's not statistically significant, so whatever. But which of these has the higher probability of being male? Now remember, we're predicting the probability of somebody being male because male comes last alphabetically. Thank you so much. I appreciate that, Kayla and Shreya. And so when you think about this in this output, take a look right here. What do you notice about this coefficient? What do you notice about the coefficient right here? Yeah, definitely, Priya. I think we could. Ooh, good stuff, Priya. We'll try to. Good questions, Priya. I think we got it. Yeah, Priya, we'll try to do that because we know low 320. We'll maybe do one more 320. We'll hop over to 201. You got it. Thank you, Priya. What do you notice about that coefficient? Like, what's the main thing to notice about it? It's positive right there. That's all we really care about. Rest of it. It doesn't matter. Thank you, Rock. It's positive. That's what's to care about it. We care about it being positive. Because it's positive, that means 2 otherwise identical people. So they're just basically the same person, but one of them has a significant other, and one of them does not. It's like I'm 2 people here. The person with a significant other would what? So we're trying to predict click-through. I thought it was churn for a second. I misspoke on what you're doing. 2 otherwise identical individuals where one has a significant other and one does not. The person with a significant other would what? Hence, I meet the criteria. 2 otherwise identical individuals. That would be 2 otherwise identical individuals where one has a significant other and one does not. The person with a significant other would be, and think because its coefficient is positive, so we're going up the curve right here. We're going this way. So they would be what? Yeah, I think I did. they're more likely to be male. Exactly. I think they're, or you could say, usually I go with the sign of the coefficient. So if I say more likely, it's because the coefficient's positive. That is true right there. Kayla, in this data was collected male, female. So I usually like to say more likely to be level of interest or less likely to be level of interest. Like it's so weird when you look at these coefficients, which this one is almost statistically significant. Not quite though. Two individuals who are otherwise identical, but one person believes they are more attractive than the other. The person who believes they're more attractive is more likely to be male. So yeah, interesting. But yeah. Yeah, and then this one right here. Two individuals who are otherwise identical. I think you're right, Kayla, right there. Two individuals who are otherwise identical, where one person has a significant other and the other person does not. The person with significant other is more likely to be male. You could say, but it's not statistically significant, so it's just like randomness. It's not, doesn't really help us. What does help us in this model is body piercings. How much do you want to weigh? How much do you weigh? And how much video games do you play? Pretty, maybe things we'd assume about the world. Doesn't mean you are male or not male if you do these things or don't do these things. But two people who are otherwise identical, where one of them plays more video games than the other, the person who plays more video games is more likely to be male. Two people, and the most significant variables are two people who are otherwise identical, where one of them has more piercings than the other. The person who has more piercings is less likely to be male. Two people who are otherwise identical, where they have different desired weights. The person who wants to weigh more is more likely to be male. Two people who are otherwise identical, where one of them weighs more than the other. The person who weighs more is less likely to be male. This one is due to randomness. It is a high p-value, but it is weird to say. Two people who are otherwise identical, where one of them is taller than the other. The person who is taller is... Wait. Okay, that makes sense. More likely to be male. Okay. Sign of the coefficients makes sense. Oh, this is weighs more. That's what the one. Did I misread this one? Two people who are otherwise identical, where one of them, which that's a very significant coefficient. Two people who are otherwise identical, where one of them weighs more than the other. The person who weighs more is less likely to be male. So interesting stuff and super significant, but multiple worlds can be interesting because sometimes the relationships don't quite make sense. You see, I don't know. I don't know how the multiple world works. Let's see. We're going to do one more 320. Then we're going to hop over there and do... Which ones did Peter want? Number 2 and 3 from the homework. You bet. Let's go back into the main screen. Chapter 16 homework coming up here in a little bit. We got one more on the docket. 1F. Do a lot of one right here. Text per day. Oh, it's text per day. The person... Two people are otherwise identical who differ in their text per day. The person who texts more is more likely to be male. Facebook, though, more likely to be female. Or less likely to be male. 1F. What does 1F say? What does 1F say? 1F. Wait, is there 1F? I don't see 1F. I don't see a 1F. People said 1F, but I don't see 1F. There's no 1F. Oh, come on, I'm an outlier. You're an outlier straight right there. I see a 2F, but I don't even see... People might have a slightly different assignment. A teacher might have changed it. I don't see 1F, 2F. Have I gone mad? Okay, well, let me know what else you're wondering about. We did a good bit of the assignment or interpretation. Who's playing sad music? Oh, we'll play a little happier music. You ready? We'll play this. There we go. Gonna do a little... If you have 320 questions, let me know. It's my hype song. One F is for sure there? I think it's activity. The activity, yeah. I know, I was like confused. Is activity due tomorrow? I need to do activity then. Like today. Might be doing a late night activity stream. I've been trying to catch up on everything, emails, Discord, everything since wedding. Thank you to everybody. It's been, no one's been mean. Like, hey, Brian, Santa, you okay up there? Freaking out, I'll be up. Awesome. Well, we'll be doing it. Let's hear it here. Stat 201, chapter 50. They've gone to sumo wrestling on the roof. Let's go check it out. Here we go. Over the main screen. Time to do it. Okay, a company is being sued for job discrimination. Awesome. I mean, I don't know. Because only 7% of the newly hired candidates were immigrants, when only 13% of all applicants were immigrants. Is this strong evidence that the company's hiring practices are discriminatory? So you gotta love Mike Pearson with all the different things. Yesterday we were doing radioactive fallout, childhood congenital abnormalities. Mike Pearson just bringing all the happy topics for us to talk about. So here we are with a lawsuit. How do we know if it's one or two-tailed? So think about what they want to look for evidence of. Would the company or the people suing be trying to show, oh, see you later, Dalen, have a great day? Would they be trying to show evidence that they're hiring like too many people, too few people, or not the right amount of people? So if you're going to sue people and say you're discriminating, would you try to say you're hiring too many people, you're hiring too few people, or you're just hiring not the right amount of people? Generally, a discrimination lawsuit would probably try to go towards what way? If you think about, if you're the lawyer, like, we are going to show evidence they did not hire enough people, hire too many people, not hire the right amount. What do you think they would say? What do you think they would say? They would say too few, right? You could, theoretically, someone could maybe say not the right amount, but we'd probably try to say, like, they're discriminating, they're not hiring enough. Like, that's like, because imagine if you said they're not hiring the right amount, and then they said, oh, but we're hiring more. And then you'd be like, oh, well, darn. So you'd probably want to show evidence they're hiring too few. Like, there's evidence that they don't hire enough individuals from this group. So that'd be discriminatory. Like, if you just had random applicants and then you hired only 7% out of the 13 from one group, it might be like, you hired less than we would have expected, given the applicants. And then you could have someone, well, then another group would sue, right? So if you only hire one group, another group might sue, and then they'd be the one saying you hired too few of our group. So from the perspective of the suer, they probably want to show a one-tailed test. Does that make sense? From the perspective, I can't even speak today. From the perspective of the person suing, they'd want to show evidence that the group they're suing in favor of was not hired at a high enough rate, that there were too few hired. I think someone just won the sumo match on the ceiling on the roof. They're doing my roof today. The one-tailed test, because yeah. So the one-tailed test, because the company's probably not going to be sued if too many were hired. Because do you think about who the lawyers are? The lawyers aren't going to come in and saying, we're suing you because you hired too many people that we represent. Now someone else could represent another group and it could be fun. Lawyers, they're fun. I have a cousin who's a lawyer. He's awesome though. I don't think he does that kind of stuff. Okay. How do we do this? Who knows the tricks? Who knows the tricks? Say it with me. I'm making a sign right here. In a type 1, so in a type 1, the null what? We're going to go to our notes from previous days all the way back. So in a type 1, and this is the best way to do it. In a type 1, the null is true and we reject it, right? I want you to look at this statement right here. And just be careful. This is where people make mistakes. I just want you to slow your mind down. I want you to look at this null hypothesis and I want you to say, this is what right now? I want you to look at it. I just want you to say it. Say, that is what right now? I just want you to look at it and say it, that is what. I want you to say it. Because where people go too quick and they say, it means this. And I say, no, just look at it. Say, I'm looking at that and that is what right now? That's a statement about reality. Somehow we know this. We are omniscient right now and we know this. That is what right now? You've just said in a type 1, what? That is, you're looking at it. Remember, we're doing type 1 right here. Here's our 1. That is truth. Does that make sense? That is true. So just tell me. Tell me about the company right now. Don't tell me too much. Just tell me about the discrimination and all this stuff. What is true about it? What do you mean it's true? Just explain to me. The null hypothesis for this court case. Just talk to me like we're not doing stats. Tell me about reality. So tell me about reality right here for this company. That's just reality, right, Kayla? According to this right now, according to this reality we're in, so it is a fact. It is true that they're not guilty. Does that make sense? But why do we call this an error? Why do we call it a type 1 error? So it is true in reality that this company right now is not guilty. But why do we call it a type 1 error? Because if that is true, it's going to be an error to reject it. So that is true, but we've rejected it. And we have said that we have evidence. Now, sometimes things you think you have evidence for, but you're wrong, right? Is this making sense right here, Priya? We reject Oh, yes. Wow, Kayla, my brain. Kayla, you're going to great job in law school. You got this. So it's like, I'm like, I don't know who I am now. I'm a classic YouTuber. So with this right here, you're right. Oh, wait, so Priya, slow me down, because let me know what you're thinking. So don't worry about the stats right now. I want you to think about this. In a type 1 error, the null is true. So just think about this. It is true that the company's not guilty. That's just a statement of fact. We're not testing it or anything right now. There's no test. There's no p-values. There's no nothing. That's a statement about reality. Does that make sense? According to what has happened in this court case. But in the court case, what did they do? What happened that was an error? Why do we call this an error? So in a type 1 error, the null is true. And exactly, and this is like saying like a hypothetical, like, because we don't really know when we make errors, because someone one time said to me, well, why would you make an error if you making an error? And you'd say you don't know. Because the company is maybe not discriminating. It might be that they have some sort of, system that they've used, and let's say it's not discriminatory, but the company's using a system, and for some reason it was just random chance that they got this many low, and maybe like the following year they have like quite closer, because random variation can produce results that are towards the bottom of what you would expect. Like you could get a random result that's unlikely. It can happen sometimes randomly. And someone will say, oh, that's discriminatory. And you're like, well, it can happen like 1% of the time. And they say, well, 1% is unlikely. And you're like, yes, but it can still happen. So, well, it's an error because we did what to the null? The null is true, and it's an error because in this court case, they whatted the null. Yep, Kayla, great job. And does that make sense, Priya and Kayla? Great job working on this together. They should not have rejected it. They should have failed to reject it. Does that make sense? If the null is true, you shouldn't reject it. Because right now, we're saying it's true that they're not guilty. It is a fact that they're not guilty. They are not guilty. That's just a fact. So in this court case now, they made an error, a type 1 error, because the null was true, and they rejected it. So you would think, well, why did they reject it? Well, they made an error. So that's the type 1 error. And remember, this is the one of it. Well, there's the one, and then we make a T out of it to say the null is true and we reject it. But good practice. We'll be doing more of this tomorrow, Monday in class. But good practice on this, and then we're going to do the type 2 here in a second. So when we go back to this, a type 1 error is deciding that the company discriminated when in fact it is not. Only 2 of these are errors, because you'll see the other error here in a second. Start check answer. Watch me get it wrong. Type 2 error. And when someone fails to reject the false null exactly, so when they should have rejected it. And that is great. Kayla and Shreya, we're earning another 1,000 points right here. Great job practicing and helping 201 practice right here. This comes down to memorization and practice. And I usually like to write my null hypothesis out. And so we're going to do the type 2 right here. Remember, in a type 2, you make the 2 right here and you make the F right here. Because in a type 2, the null is what? In a type 2, you look at this null hypothesis and say, this is a what statement? You would look at that null and say, that is a what statement in a type 2 error. And so you know the truth right now. You're saying that statement is a what statement? That statement is false. Now be careful. You say, oh, it's false, I should reject it, right? And since we're going to make an error, we're going to do what right here? And so notice how you have your F right here from the type 2, because we're making the F right here for the type 2. And then what are you going to do? You are going to fail to reject it. So it is false that the company is not guilty. Can you retranslate that? It is false that the company is not guilty. When I say they're not guilty, that's a false statement. Retranslate that. Put that into normal lingo. It is false that the company is not guilty. It is false that the company is not guilty. Put that in normal people talk, not stats talk. It is false that the company is not guilty. Not guilty, that's a false statement. So what does that mean? They are guilty, right? Because saying they're not guilty is false. So they actually are guilty. But the problem is we've made an error here because remember, they are guilty. We're saying it is false that they are not guilty. And then we failed to reject the null that they are not guilty. So there's a lot of nots and everything in here. And so I think it can help to visualize it because we're not rejecting this. We're staying with it. So I like to say I do not reject. So in a type 2, you do not reject the null. You fail to reject it. So at the end of this court case, they're going to come out what? In a type 2 error at the end of this court case, what's going to happen to the company? So explain to me in a type 2 error where the null is false. So it's false that they're not guilty. They are guilty. It's false that they are not guilty. So they are guilty. But we are going to fail to reject the null. So what's going to happen at the end of this? Remember, they are guilty. Careful. Because we're going to fail to reject the null. We're not going to reject it. They get out of it. Does that make sense? So if you're a 320 everything, that is correct, Kayla. Exactly. This company discriminated, and then they're like, well, we didn't reject it. We don't have enough evidence. So does that make sense? They're going to come out not guilty, but they are guilty because the null is false. In a type 2, the null is false. They are guilty. This is a false statement. The truth is this. Now, I don't usually mention truth here because that messes up. In a type 1, the null is true. In a type 2, the null is false. But you could think about if the null is false, then the alternative is true. Because, does that make sense? If the null is false, the alternative is true. In a type 2, the null is false, and we fail to reject it because the alternative is true. Because one of these things has to be true. Either they're guilty or not guilty. Is this making sense, Priya and everybody? And I don't say this lightly. Type 1 and type 2 error are very important in all of statistical ideas. It's when we make mistakes with our results. So it's not just 201 that needs to know this. It's 474, 475, 320. Type 1, type 2 error is super important. Sure, an interview could ask you about this. So it's important to understand in a type 1, the null is true and we reject it. And type 2, the null is false and we fail to reject it. And then think about the implications of it. Because especially for students, we'll do one last quick example here and then we'll finish off the problem. And then we'll do the next one. One of my classic examples is I want you to think of which of these is worse. So we have the null hypothesis of not cheating and the alternative is still like guilty. So be careful. This is good of cheating. And yeah, was it? Was it, Treya? Not shocked they did. I didn't know that. Is that true? If they did that, I am not shocked. Because it's good practice. It's real stuff. It's real application. Like, what is the implications of it? Could be, maybe. I don't know. I don't know what they ask. If you told me that, I'd be like, oh, I'm not shocked. It's a big, important concept in statistics, type 1 and type 2 error. So when you think about this, be very careful in how you answer this. Think about student versus teacher. Which one of these errors? Now, I'm a nice teacher. You got awesome, Shreya. So good to hear that. Yeah, you're working great. You've got great, yeah. Which of these errors would be worse? Now be careful, a type 1 or type 2 error. And we'll just talk about this briefly and we'll finish off the question. Which one of these errors we usually assume without evidence that someone's not cheating? Which one of these errors would be worse? So your teacher's looking at your paper and being like, You're not sure. Which one of these errors would be worse? A type 1 or type 2 error? Maybe I should go to law school. I wanted to go to law school when I was younger, Kayla. When I was younger. So in a type 2 error, the null is false. So what happened in the type 2 error right here? That's a false statement. Magic color change pen is back. And we fail to reject it. In a type 2 error, what happened? In a type 2 error, the null was false and we failed to reject it. So explain to me just normally, like, oh, my friend this. What happened to your friend? Maybe your friend was in a type 2 error. And so we'll see something interesting here, which is very important about type 1, type 2 error. And what would be going on right here? In a type 2 error, the null is false and we fail to reject it. So what happened to your friend? The null was false and they failed to reject it for your friend. So it is false that they did not cheat. So what did your friend do? And then they failed to reject the null. So what did they decide? We're doing the type 2 right now and thinking about the implications of this and understanding the context. That's the 2. The null is false and we fail to reject it. Your friend was cheating, right? Because the null is false. The null is false. Your friend did cheat. And your friend got away with it. So maybe you're like, cheating is bad. My friend should get caught. Your friend cheated but didn't get caught. So that's the type 2. How about the type 1, though? The type 1, the null is true, but we what the null. So now, in a type 1, the null is true. Just look at your friend did not cheat. That is a true statement. This is another friend who didn't cheat. So now this friend is in a type 1 error where they did not cheat, and then they got in trouble. But if you think about this from your friend perspective, the type 1's way worse. Now, I'm not saying I'm a mean teacher. But for a teacher, they might never know that somebody they got in trouble didn't really get in trouble or like didn't really do it. So a teacher might say, you know what, I want to catch all the cheaters. I'm more worried about my type 2 error where the null is false, but I don't reject it. I'm worried about people getting away with cheating. So type 1, type 2 error is very what? It's very subjective on which one is worse. Think about this. If my sister, who does real estate, is trying to sell a home, her null hypothesis might be don't market to someone. Like she's going to send out a marketing thing that costs her like $20 to make. And she needs evidence to market, right? So she's not just going to spend money willy-nilly on everything. She's going to say, I need evidence that I'm going to get a return, right? So what would a type 1 error, can you explain to me? You'll really know it if you think about this. What would a type 1 error be? So my sister is trying to figure out a new market. She's trying to figure out if she should invest in this. She needs evidence to invest. What would the type 1 error be? And then we're going to finish off the question. So her null hypothesis is she needs to have evidence, or her null is that she's not going to spend money until she has evidence that she should put her money out there and start doing it. What would a type 1 error be? So what would a type, can you explain to me just kind of in words what the type 1 would be? So her null hypothesis is she should not market and spend money on doing marketing materials and stuff unless she has evidence, which is the alternative she's looking for evidence for. So what would type 1 be? So always look at your null and say the null is true. Yeah, Shreya, 500 points right there. Wait. Yeah, I think Priya, I think you got it right there. Sorry, I thought I saw Shreya was before you. Priya, great job right there. Yep, Priya, thank you so much, everybody. 500 points in the chat. So I think Priya got it perfectly right there. Priya said she shouldn't spend money, but she does. Correct. Because if you look at this, the null is true in the type 1, right? It's true that she should not spend money. But what did she do to her null hypothesis? Because she made an error. It's true that she should not be spending money on this. What did she do in this type 1 error? So it's true she should not be spending money on this. Like that is the truth. She shouldn't. That's the truth. We somehow know it. Don't know how we know it. She rejected it. Great job, Priya, right there. She rejected it, and so she rejected the null right here, and so she rejected it, and she spent money. So this would be not spending money properly. Like she wasted money. Now in a type 2 error, the null is false, and we fail to reject it. So type 1, she lost money. Type 2, the null is false, and we fail to reject it. So that's a false statement. So on type 2, she misses out on an opportunity. Does that make sense? Because in a type 2, it is false that she shouldn't market. She should, but she doesn't reject the null. So type 2 is when she's like, I don't know, I guess I won't spend money. And then she misses out on an opportunity. So type 1 in this scenario would be her spending money when she shouldn't. Type 2 would be her not spending money when she should. Does that make sense? The more practice you get with these, the more you get used to looking at the null and saying the null is true, the null is false, and making conclusions from them. But that leads to, we'll finish off the question. We'll do the next one here pretty quick. But a type 2 would be, let me look at the other one. We talked about it. The side the company is not discriminating. Yeah, type 2 are the fail to reject the false null when they are, not discriminating when they are. When we got a little power stuff down here, I think, at the end. Oh, definitely more practice in class. These are good. These are just memorization type ones. Good practice. The power of the test. Power is defined as the ability to correctly reject the false null. Literally write this down. Power is the ability to correctly reject the false null. That's textbook. Put that on a note card. I've seen it on the test just by that. Power is defined as 1 minus beta, i.e. not making a type 2 error, and we'll be going over there. One way to memorize what alpha and beta are is 1, 2, A, B, plus, minus. Type 1 error is controlled by your alpha level. Type 2 error is controlled by your beta level. Type 1 error I often call a false positive, like finding out the company discriminated when they really didn't. False positive, like doctor says you have scurvy, more on Tiny Brian tomorrow, when you don't, like a false positive for a test. And type 2 error is failing to find results, so a false negative, and associated with beta. So this is the complement of a type 2 error, and that is power. So this right here is the equation for power. So it's the ability to find results, or textbook, the ability to correctly reject the false null. So the power of the test is the probability of rejecting the false null, so to correctly determine discrimination. So they're trying to find evidence. If the null is false, they're trying to find that they're discriminating. So power is a probability calculation of the ability to correctly reject the false null. I think that's got it. Got a little bit scared. We're good. If they were tested at the 5% instead of the 1%. So this goes to alpha and how it impacts power. If you increase alpha, you decrease power. They're inversely related. So since the power of the test would decrease because the level of significance increased. Let me see here. The power of this would decrease. That looks good. Oh my gosh. Let me reread it. Oh my gosh. Wait. Brain work. Okay. No, if you increase alpha, you increase power. You decrease beta. I've drawn this out 1,000 times and my brain's not on. All right, so the power of the test would increase because we're increasing alpha. If you increase alpha, alpha is your rejection criteria. My brain's not working. So if the power of the test would increase because we increase the level of significance increase. So I had to click the decrease now. Just to draw this out really quickly. Oh, really? And that's sample size. Here, let me draw this out. The way this drawing goes is the following. There are 3 things that impact power. There's sample size, there's alpha, and there's effect size. Any increase to these would decrease beta. And think about this, if power, exactly, I made a mistake. Oh yeah, so you see if any of those increase, they decrease beta. You remember how power is 1 minus beta? So if you decrease beta, you do what to power? Since increasing any of these, and we'll go into more detail, since increasing any of these decrease beta, like larger sample size, larger alpha, since any of those decrease beta, what would you do to the complement of beta? Does that make sense? So if you increase sample size, beta goes down. If you increase alpha, which that problem was, beta goes down. If you have a larger effect size, you don't really control effect size, beta goes down. And since it's the complement is power, then they follow. So if you look at the way the arrows go, it literally would be increasing sample size increases power, increasing alpha increases power, increasing a larger effect size. We don't really control that one, increases power. But all of these also decrease beta, and the complement of beta is power. So by decreasing beta, you are increasing power. Yeah, no, don't worry. I got it wrong. My brain just blinked for a moment, and I was like, wait a minute. Yeah, we're increasing power. They're all inversely related to beta, but positively related to power. Do know this. So power is, oh no, beta, yep. And beta is type 2 error. Beta is the probability of your type 2 error, and alpha is your probability of your type 1 error. So alpha is the amount of times you reject the true null. So your alpha level that you pick is going to control your type 1 error rate. Does that make sense? And then alpha and beta are not complements, though. That's a test question sometimes too. It's just that beta can be found via power curves and such. We don't do those calculations in our class. So don't worry about finding beta, but do realize that if you increase your alpha, you will decrease your beta. See you in class, Kayla. We'll be there in 14 minutes. But this has basically been a lot of the lecture, Priya. I'll draw this out again tomorrow here, talking about how if you have a larger sample size, your test is more powerful, because this right here is known as power. That value is what we call power. And power is the ability to find results. Imagine this, Priya. When do you think you'd have a better idea of a medical study? If you did a medical study with 10 patients or 1,000 patients? Oh, not tomorrow. Monday. If you did a medical study with 10 patients or 1,000 patients, when would you have a better ability to find results, which is what power is? When would you have a better ability to find results with 10 patients or 1,000 patients? When would you have a more powerful test? Go to Treya, go power up for class. You got this. If you did a study with 10 patients versus 1,000 patients, when would it more patients, right? So that would mean you have a better ability to find results. Like maybe you're testing 2 drugs and you want to see if there's a difference. So the ability to find results would be easier, or a higher ability with a larger sample size. We generally don't mess with the alpha, but you could make your alpha level higher, which means you reject more often. Like alpha is the point at which you reject. And if you want to reject the null, not suggested, you could change your alpha. And then the effect size is dictated by the true difference between the null and the truth. So if the drug is super powerful, it's going to be easy to detect. But if there's a small difference, like a small effect, like imagine this is a miracle drug. Do you think it'd be very easy to detect that? Like this drug, like we find a drug that let's say cures everyone of cancer. Yay! Let's end on a happy note here. Do you think that'd be easy to detect? We just give them this one pill and then they're magically cured. And we're like, whoa, yesterday they were on the bed and now they're doing gymnastics, which they didn't do before. That'd be a pretty big effect, right? And that's what we're talking about here when we say effect size, the difference, which we don't have a way of knowing it. We can just kind of estimate it by what we see. So if there was a big effect, that'd be good. Like that'd be easy to detect. The test is called powerful. Like it's easy to detect that this is there's a difference. But let's say the drug actually helps 1 in a million people. And although that sounds like it could just be random, if it only helps 1 in a million people, that'd be very hard to detect. And we'd probably need a large sample size to see it. It's very unlikely that we would know that the drug is actually doing anything, and we'd probably make a what? So Priya, another 1,000 points. If the drug probably, like, let's say it's very hard to detect, but the drug actually works, but it's very hard to detect, we'd probably make a what? Yep, Priya, good work right there. And we'd probably make a what if the drug, like, really doesn't, it does something, but it's very hard to detect. We'd probably make a what as we're looking to show that the drug does something. We get 1,000 points right. We'd probably make a what? What do you think we'd probably make if we're trying to figure out, does this drug actually do anything? And it does something, but it's very hard to detect. We'd probably make a what? We'd probably make a what looking for the drug doing what it does. Like, we probably wouldn't find out that it does. We'd probably be like, oh, well, I guess it doesn't do anything. Like, it'd be very hard to find that. Like, it has a very small effect. Like, so small, it only helps like 1 in 10,000 people. And so we'd probably make a what looking for it, because we probably wouldn't find it. We'd be like, I guess, I don't know, it doesn't really do anything. Guess it's the same as the other drug. We'd probably make a error. We'd probably fail to reject the false null. So the drug does something, but we don't find it because it has a small effect. Does that make sense, Priya? We'd probably fail to find the results. I'll give you 1,000 points right there. So we probably wouldn't find it. We'd be like, darn it. Like, I guess the drug doesn't do anything. If the lawsuit was based on 32 employees, how would it be based on if it was based on 10? Good work, Priya, right there. Sorry, all the names bounced from my head. Getting ready to teach here in a moment. So if it was based on 32, then it would have a larger sample size. The power of the test would be higher because the sample size increases. Boop. So no worries. These are a lot of terms we're throwing around. We're going to do more examples tomorrow. Do we have time to speed run the next one? Let's do it really quick. You ready? 900 working men, 9%. So we need to do, we got 9% right here. P hat times Q hat over N square root. Does that make sense? P hat times Q hat over N square root. So that's the standard error. Times 1.645 is the oh my gosh, times 1.96, 95% confidence, because this is a Z interval. That's the margin of error. So the margin of error is 1.9. People banging on the roof. There's that. What does the confidence interval say about the pundit's hypothesis? They believe 6%. No, because 6% is not in the interval. We have strong evidence that more than 6%. Yes. So that's using the connection between confidence intervals and tests. This equation right here is, and I'll write it down so you can see the one I ran. The equation I used for that was p hat plus or minus z, p hat q hat over n square root. Does that make sense, Trey, right there? You saw the announcement. But you want to use your p hat. Mine was 0.09, q hat 0.91, and sample size was 900. Z-score was 1.96 for 95% confidence. And then I found the margin of error, added subtractive, and saw the value was on the interval. But Priya, great work. The confidence interval equation, there it is right there. And that's the standard error, sample size, p hat, q hat, and Z star for the 1.96 for 95% confidence. Make sure to look up the Z star. If not, I'm going to head off. But let me know if you have questions. Class in 7 minutes. Thank you, Priya, so much, and great work. Excellent job practicing. You got this. Bye for now, Priya. Bye. Class starting soon.